recording in progress. And okay, so please, Stefan, we are interested in your recent work, which is almost always oriented at the fundamental questions of formal reaction kinetics, and you regularly return to the founding fathers. So
exactly, yeah, this will be the next slide.
okay.
Yes. Thanks, Janos, for giving me the opportunity to speak in your seminar and to all the organizers. Yeah, the title is From Complex Balanced Mass Action Systems to Binomial Differential Inclusions. So, okay, oops. So, I mean, complex balanced mass action systems have played an important role in the history of chemical reaction network theory. They were the subject of these famous 1972 papers by Horn and Jackson. And so the most important property of a mass action system with a positive complex balance equilibrium is that the reaction network must be weakly reversible. Then the given equilibrium is asymptotically stable. And in fact, all equilibria must be complex balanced. And this is shown by using the entropy as a Lyapunov function. And then the last famous statement is that there exists a unique positive, necessarily complex balanced equilibrium in every forward invariant set, also called compatibility class. And this statement was later called Birch's theorem. So so to speak, in my history, I did not investigate mass action systems per se, but we were interested in generalized mass action systems. And for quite some time, we studied uniqueness or unique existence of complex balanced equilibria, but for these generalized mass action systems. And we could characterize those properties by equivalent conditions which involve sign vectors. And only later we studied stability of complex balanced equilibria. And in the beginning, we tried to, again, show asymptotic stability, but for several reasons, this did not work out very well. So we turned to linear stability. And in this paper from last year, we gave sufficient, also mostly sign vector conditions for linear stability of complex balanced equilibria for all rate constants. Maybe I should mention, before that, we also with Balázs Boros, we looked at necessary conditions. And already there we saw, okay, it will be difficult to find equivalent conditions. So now we have a paper on necessary and on sufficient conditions. So how did we do this? I mean, there we showed, or we gave conditions such that the negative of the Jacobian on these forward invariant sets, which is then called the scaled Jacobian or reduced Jacobian, is a p-matrix and sign symmetric. And as the main technical tools, we use cyclic decomposition of the graph, which is a standard result used by many people in our community. But what is the new thing that I developed is another decomposition of the graph Laplacian. And this fits very well with what we call monomial evaluation orders. So, but today I will talk, in the beginning, I will talk about this new decomposition of the graph Laplacian, but I don't show the application to generalized mass action. But it's also very helpful to understand the structure of the mass action systems, of the most important kinetic system. So it helps to understand the binomial structure of mass action systems, and it suggests to define a more general class of dynamical systems called binomial differential inclusions. And maybe the bottom line message of this whole talk is that this very general class of dynamical systems is, or can be shown to be asymptotically stable. with the use of the entropy of the Lyapunov as the Lyapunov function. So to speak, it exhausts the power of the entropy as a Lyapunov function. So you see the motivation was generalized mass action kinetics. Then there is this technical result about the graph Laplacian, and the application is mass action, not generalized mass action. So there is a first part, which I'm not so sure if it's really necessary in this seminar, where I explain reaction networks, mass action systems, and complex balance. In the second part, I show this new decomposition of the graph Laplacian and what it means for the binomial structure of mass action systems. Then I define like monomial evaluation orders, which defines regions in the positive orthant. And in logarithmic coordinates, it defines polyhedral cones. So if you are familiar with the proof of the global attractor conjecture by George Grachun, this is very much related to his definitions. And in the last section, I finally define these differential inclusions. I show how complex balanced mass action systems can be included, and that these differential inclusions are asymptotically stable, and hence also complex balanced equilibrium of mass action systems are asymptotically stable, but that's not new, right? This we know since 50 years. So what's reaction networks? Over the years, my view changed. So now I see there's a modeling framework for many fields: chemistry, biology, economics, and even engineering. And one reason is that every power law dynamical system can be written as a reaction network with classical or with generalized mass action kinetics. So there are also many definitions of reaction networks. I mean, the simplest is just a reaction network is a set of reactions. So what are reactions? So it's a set of ordered pairs of formal sums of species. So ordered pairs, so left and right-hand sides of the reactions. Like an example, we have 4 species, A, B, C, D, and 1, 2, 3, 4, 5, 6 reactions. But where's the network, right? You're asking then. So when we draw the reactions, then suddenly we see a network, also called the complex reaction graph, which is induced by the reaction network. The components of the graph are called linkage classes traditionally. If the components are strongly connected, then the network is called weakly reversible. Just to mention these notions. Georg Regensburg and me, since we studied generalized mass action, we use a different definition. We say a reaction network is a graph to begin with, and then a map that assigns to vertices so-called complexes, right? We start, in this example from before, we start with the graph. The vertices are just labeled with numbers, and then we assign to every vertex a complex, like a formal sum of species. And why do we do this? Because to this graph, we don't just assign the stoichiometric complexes, but also the kinetic order complexes. So for us, it doesn't make sense to identify the vertices with the complexes because we want to assign 2 types of complexes to the vertices. For the talk today, this does not matter because we stay in mass action kinetics. So now what happens in a reaction is also called stoichiometry. Yes, you have a formal sum on the left, formal sum of the right, but that does not look so nice. So we write this as y goes to y prime, but y and y prime are just some vectors in Rn, if there are n species. And the y prime minus y is the net reaction vector. So in the example, 1a plus 1b goes to 1c. The vector y is the vector 1, 1, 0, and zeros. And the vector y prime is 0, 0, 1, and some zeros. And the reaction and the net reaction vector is minus 1, minus 1, 1, right? 1a is consumed, 1b is consumed, and 1c is produced. This was the geometry. Now comes kinetics, which says how fast a reaction happens. The rate of the reaction depends on the concentrations of the species. And the most important kinetics, at least from a theoretical point of view, is mass action kinetics. And there, the interesting thing is that the kinetics is determined by a constant and by the educt complex, by the complex on the left, namely via the monomial x to the y. So that the stuff that is consumed determines the speed of the reaction, with the stoichiometric coefficients being the kinetic orders of the concentrations. So for example, again, for 1A plus 1B goes to C, the rate is a constant proportional to the concentration of A to the power of 1 times concentration of B to the power of 1. And in generalized mass action kinetics, those two exponents need not be 1, but they could be A and B, arbitrary real numbers. So formally, a mass action system is a triple. We have a graph, a map Y that assigns to every vertex a complex, and a map K that assigns to every edge a positive number, namely the reaction rate. Then we can define the ODE. dx over dt is a sum over all edges, meaning the reactions, the net reaction vector times the kinetics, which is here k x to the y, because we use mass action kinetics. Then you can decompose the right-hand side in several ways, because, yeah, so you can decompose the right-hand side into the product of 4 matrices times a vector of monomials. The first matrix is the complex matrix, then comes the incidence matrix of a graph, then a diagonal matrix with the rate constants, then a so-called source matrix. And you can combine the first two matrices, there as the stoichiometric matrix, and the middle 3 matrices are the Laplacian matrix. That's nice. So in the example, again, our network with 2 connected components. So either you have stoichiometric matrix times vector of rates, or complex matrix times Laplacian times a vector of naked monomials, so to speak. Yeah, if I'm too fast, please stop me. Now, the last thing in this first part is the definition of equilibrium. So the positive equilibria are all positive x, such that the right-hand side of the ODE is 0. But the complex balanced equilibria are all x where already Laplacian matrix times x to the y equals 0. So that's a subset of the equilibria, an important subset. And as I showed on the first slide, if such a positive equilibrium exists, then the underlying graph is weakly reversible, the equilibrium is asymptotically stable, all equilibria are complex balanced, and in every forward invariant set, there is such a unique positive complex balanced equilibrium. That's why this is so important. Okay, now let's go to the graph theory part, to the Laplacian matrix. I mean, graph theory is quite divided. I mean, the Laplacian matrix is also defined for undirected graphs. There you can use it via the matrix tree theorem to compute the number of spanning trees. But for dynamical systems, one often looks at directed graphs. Like, for example, in the Kolmogorov forward equation, also called the chemical master equation, the rate matrix is an infinite dimensional graph Laplacian. But probabilists don't normally mention this. Then let's stay in the finite case. When we have a simple directed graph, we could view the vertices as states with probabilities, psi, and the edges as transitions between these states, with a rate matrix K, which is defined like this. I mean, if there is an edge between 2 nodes, then there is a finite transition rate. And if there is no edge, then no transition is possible, so it's 0. And then you can write the time development of the probabilities as d psi over dt is Laplacian matrix times psi. And the Laplacian matrix is the transpose of this rate matrix minus a diagonal matrix that comes from multiplying the rate matrix by a vector of 1s. And here you already see that the Laplacian matrix has a left kernel vector, which is the vector of all 1s. When I multiply here with 1s, then this becomes 0. Anyway, these are simple linear systems one can study with the Laplacian matrix. In reaction networks, we do something else, of course. There also, we don't use this rate matrix, which assigns rate constants for pairs of vertices, but we assign rate constants to edges. And then we can decompose the Laplacian matrix as we have already seen before. It's the incidence matrix times the diagonal matrix with the rate constants times the source matrix. Yeah, so an important property of the Laplacian matrix is that if it's strongly connected, then the kernel of the Laplacian matrix is one-dimensional. And you can write it like this. It's the image of a vector capital K, which is the vector of three constants. So for every vertex, you can define a tree constant. And how do you do this? You must sum over all spanning trees that are rooted in this vertex. And then you multiply up all the rate constants on this spanning tree. Which these expressions can become very large for large graphs. And what you can do then is you can multiply the Laplacian matrix with a diagonal matrix that contains those three constants. And then you get a doubly stochastic matrix, which means it has in the vector of ones in the left kernel and also in the right kernel. So in the left kernel, we have already seen it. When we multiply with a vector of ones from the left, the matrix AK, then it's 0. But when you multiply with the vector of ones from the right, then a vector of ones multiplied with a diagonal matrix of K is actually just K, and A times K is 0. Because the kernel of AK is the image of this vector. Yeah, I could say more about doubly stochastic matrices. With Balázs Porras, we looked into this at the time, but it's for my talk today, this is not so important. Okay, let's go to an example, right? Let's consider the left connected component of our example. It was for 4 vertices, 4 edges. What is the incidence matrix? Right, it says for every edge, from where to where am I going? Like I go here, the edge from 1, 2, I go from 1 to 2. In the edge 2, 1, I go from 2 to 1, and so on. The source matrix says what is the source of this edge. So the first edge starts from 1, the second starts from 1, the third edge also starts from 2, the third reaction 2, 3 also starts from 2, and the last reaction starts from 3. Then I can compute from this and the diagonal matrix of the rate constants, I can compute the Laplacian matrix. Then I can compute the vector of three constants, which is the kernel vector of the Laplacian matrix. And here you see, I mean, that the second and third entry are trivial, but in the first entry, you see that this is a sum over the spanning trees that are rooted in the vertex 1. Like you have a spanning tree that starts from 2, goes from 2 to 3, and from 3 to 1. So I have K2, 3, K3, 1. But there's another spanning tree if I go from 2 to 1 or from 3 to 1. So we have K2, 1, K3, 1. And then I form this doubly stochastic matrix. And I don't have to do this, but it has a nice cycle decomposition. So you see this graph has a small cycle from 1 to 2 and back. This is the second matrix. And it has a large cycle from 1 to 2, from 2 to 3, from 3 to 1. This is the first expression. Okay, this was this doubly stochastic matrix. Now to the new thing, a new decomposition. So for my given graph, I define an auxiliary graph, which has one edge less than vertices. But the edges can be arbitrary. They don't need to be included in the graph, in the original graph. I just take v minus 1 edges. So it's kind of a spanning tree but this spanning tree need not be a subgraph of the original tree. It also need not be directed. It's just I could take any set of v minus 1 edges that give a connected graph. And this, of course, this new graph G calligraphic E also has an incidence matrix, IE. And now I have this main result for the new decomposition. Like when I have a graph, a strongly connected labeled simple D graph, and an auxiliary graph, then there exists a unique matrix that is invertible. I call it here calligraphic AK, calligraphic E, call it the core matrix of the graph Laplacian. And this matrix fulfills that our doubly stochastic matrix is the product of minus the incidence matrix times this core matrix times this incidence matrix transpose. So I kind of symmetrize the doubly stochastic matrix on the left-hand side. Although this matrix A need not be symmetric. I make it a bit more symmetric, right? And now there's one more twist. I mean, this result holds for any auxiliary graph, but certain auxiliary graphs are more helpful, namely chain graphs, right? For a given graph with V vertices, I just bring them in a certain order. I define a chain, I start from some vertex, I go to the next vertex, and so on until I've visited all vertices. That's a chain graph. And then what I can show is that this core matrix, this invertible matrix, is non-negative and has a positive diagonal. And this will then later be used to show asymptotic stability of binomial differential inclusions. That's the important property. So to see it in an example, let's go back to our little graph. It has 3 vertices. So there are 6 possible chain graphs. Like I can start in 3 positions and then I can go to 2, and that's the last one. I don't have any choice. To write the doubly stochastic matrix like this. For example, if I choose this order from 1 to 2 and from 2 to 3, this has this incidence matrix and this core Laplacian. But I could use another order. For example, I go from 1 to 3, which is not contained in the original graph, and then I go from 3 to 2, which is also not contained, but it doesn't matter. I can just use any chain. Then the incidence matrix looks like this, and the core matrix looks like this. So, and why is this important for mass action systems? Because I can rewrite now the right-hand side of my ODE. If for the Laplacian matrix, I write now this IE, AK, E, IE transpose divided by the diagonal matrix, then the 3 terms to the right define a vector of binomials. So this IE transpose diag k x to the y is just this part. So the monomials are divided by the 3 constants and then differences are taken. So when I show you component-wise, then it's best visible, right? So one component of this vector B is just the monomial x to the y I prime divided by the corresponding 3 constant minus x to the y divided by the corresponding 3 constant. And this for every edge in the auxiliary graph, for every edge in the chain. So what we get is, because we have this decomposition, and this is just a matrix, it means that dx over dt is a sum of binomials. And when you look at reversible systems, then this is clear from the definition. You have a sum of binomials, and then the equilibrium constants play a role. But here, if it's not a reversible system, but a weakly reversible system, but instead of the equilibrium constants, those three constants pop up, and still the right-hand side of the ODE is a sum of clearly defined binomials. So let's look at complex balance. So complex balance means not just the right-hand side is zero, but ak x to the y is zero. Then by the decomposition shown before, this means that this term is zero, the incidence matrix times the core matrix times the vector of binomials. And since those two matrices don't have anything in their kernel, this is equivalent to B being zero. And this is now a new way to show that, I mean, complex balanced equilibria are given by binomials, because the B vector at the complex balanced equilibrium is just given by those equations. So this difference vector for a complex balanced equilibrium looks like this. And I can use this equality now to rewrite the difference vector for an arbitrary x.
Excuse me, Stefan. Here, the problem is that it is not too easy to calculate these three numbers, right?
Yes, that's
otherwise it would be trivial to solve.
Exactly. So in the next step, this is done, right? Because look here, you're saying, okay, you have this monomial differences, and you divide by the three constants. But the three constants are hard to compute.
Yes.
But here, via this equation, I can express the three constants by the monomials at the complex balanced equilibrium. And so the vector of differences can also be written like this. I eliminate the capital K's by the x stars, by the complex balanced equilibrium. Okay, you can say it's cheating. You also need to compute the complex balanced equilibrium.
Yes.
But I mean, this is the transformation that is typically done. And as a final result, so to speak, a complex balanced mass action system can be written like this. It looks, let's say, at most symmetric, right? You have this core matrix in the middle, then you have this incidence matrix of the auxiliary graphs to the left and to the right. Then you have minus y here, or y here, and x to the y on the other side. And this form I will use later. But you see already, I mean, here in this ODE, you see the crucial thing are these differences of monomials, these binomials. And especially the sign of them is important, right? Is this monomial, or where is this monomial larger than this monomial? And this I will do this I will look at in the next part. So again, the best thing is to consider a chain graph, which is a natural encoding for an order. And such a chain graph actually encodes an order on the monomials. I just say B, name B, this vector of binomials is greater equals 0. This defines a region in the state space where the monomials are ordered, because if I rewrite this vector inequality, again, component-wise, then I see it has this meaning. The first monomial, the first scaled monomial is smaller than the second, and so on, is smaller than the last monomial. So, and the region where this holds is called a stratum, and George Grachun jokingly called it banana in some of his talks. This is actually the region in the positive orthant where the monomials have this order, right? You go to an X, you compute all the monomials, and you see, it has this order. And in a different point, it has a different order. And when you take the logarithm, then those regions are not bounded by curves, but by straight lines and planes. so then which define a polyhedral cone. So here we look at all, not positive x, but at all set in Rn, such that the logarithm of this equation is fulfilled, where z is the logarithm of x over x star, right? So now this is a bit abstract, but let's go back to the example. Now, again, we have three vertices, but now let's assign a bit different monomials, complexes to them. The first one should be the vector 2, 1, the second one 0, 2, the third one 1, 0. So the first monomial is x1 squared, x2. The second one is x2 squared, and the last monomial is x1. And now for simplicity, let's assume that this complex balanced equilibrium, the scaling, so to speak, is also trivial, like it's the 1, 1 vector. Then let's look at one auxiliary graph, a chain graph, 1, 2, 3, which means first monomial smaller than second monomial, smaller than third monomial. And how does this look now? Finally, you can see what's really going on. I plot the lines where the first and the second monomial are the same, where they agree, the third and the third, and so on. And then you see here is a region where the second one is larger than the first, and where the third one is larger than the second. So you have here in this gray field, this stratum or this banana, you have exactly this ordering on the monomials. And when you take the logarithm, then this area becomes a cone. Right? You have the strata in the positive ordinate. This is the state space. But when you take the logarithm, you get this hyperplane arrangement, where the lines always show where two monomials are the same. Yeah, and this I want to use now to define my binomial differential inclusions. So we have already seen the ODE looks like this, and I give now a shorthand for this. This is FK of X. This is the right-hand side of the ODE for a complex balanced mass action system with complex balanced equilibrium X star. And then I consider an X in a certain given banana, right here. I consider an X somewhere here, which means the logarithm of ln X over X star lies here. And then I say, when I'm in this region, that the X over dt is not given now anymore by an equality sign, but lies in this set, which is the polar cone of the cone CE. Right? So first of all, I coded this red, right? So this was an ODE, the right-hand dx over dt equals something. Now a differential inclusion means dx over t lies in some set. So you can, so to speak, the dynamics can choose where it wants to go next and with which speed in a certain set, which here is the polar of the cone CE. So again, a picture says more than 1,000 words. So if I'm somewhere in my stratum, I am in this point ln x over x star in the logarithmic space. And now my dynamical system tells me the x over t lies in the polar cone of the cone CE. So I can go in the next step of my dynamical system, I can go anywhere here in the gray area, which is the polar cone of this area. So this area is this cone CE, and this area is the polar cone of that. I don't explain what the polar cone is, but you see more or less what's going on. So that's the definition. Okay, that's a simplified version of my definition of a binomial differential inclusion. That gives you the main idea. Of course, there are some technicalities. What happens if I'm on the boundary of such a region, right? If I'm on the boundary of the banana, also the right-hand side should not be just in the gray area, but it's in its interior or so. I mean, but these are details, right? The main message is if you are here in the cone, logarithmic-wise, the dx over dt is in the gray area. And now what we can show is that the right-hand side of the ODE, of the complex balanced mass action system, lies inside this cone. So the ODE just gives one particular choice of a direction of this binomial differential inclusion. So I can say it's embedded. So more technically, I say when I have a complex balanced mass action system and a chain graph and a stratum, then for all x in the stratum, the right-hand side of the ODE lies in the right-hand side of the differential inclusion. And the proof uses this new decomposition of the graph Laplacian. So when we start with a point in a stratum and some vector in the corresponding cone, then I form the term U transpose F. Then I write out the right-hand side involving the core matrix and the incidence matrices of the chain graph. And then I say all to the left of AK is a vector A, and all to the right of AK is a vector B. And just by the definition of the stratum and the corresponding cone, they are non-negative. This is just how I defined this strata. But now, since this core matrix is non-negative and has positive diagonal, this product U transpose F is always, and since I have a minus here, is always less equal 0. Which means that the right-hand side of the ODE lies in the polar of the cone CE. Of course, I mean, this is just to give you the idea. I mean, the definition of the binomial differential inclusion is a bit more complicated. And then the proofs also become a bit more complicated, but not very much more complicated. So the full truth, so to speak, about the binomial differential inclusion is what do you need to define it? You need just an equilibrium and a hyperplane arrangement, or more generally a polyhedral fan, which consists of these cones, of several cones, CE, let's number them by CE. And it can have a linearity space, but this maybe is a complication I don't need to go into detail here. Yeah, I mean, if you have a linearity space, then you don't have just one equilibrium, but exponential manifold of equilibria. And then the binomial differential inclusion is defined like this. So the direction where you go, or the right-hand side where you go, lies in f of ln x over x star. So here the equilibrium enters. So for a given x, I form ln x over x star, and this I feed into the function f. And the function f looks like this. If the argument of f lies in S orthogonal, which means that x was an equilibrium, then f of u is just a zero set, which means that dynamics cannot go anywhere. So that's an equilibrium. Otherwise, you must check, okay, this vector u, in which cone CE does it lie? If it lies in several, then you form the polar cone of all of them and intersect them, and then you take the relative interior of that to take care of the boundary cases. And still, even for this full definition, you can show that every complex balanced mass action system can be embedded in a binomial differential inclusion. So this was, so to speak, yeah, this is the statement I gave you before, just in more detail. And why is this important? Because you can show that these binomial differential inclusions are asymptotically stable. So you start with an equilibrium, define the entropy as a Lyapunov function, you know this expression. Its derivative is also this known expression, the logarithm of x over x star transpose times the time derivative. So what you need to show is that the time derivative, so the product of the logarithm with the time derivative, is strictly negative. Then you are done. Then you always go closer and closer to the equilibrium because the entropy is strictly decreasing. And indeed, one can show this. If you have a binomial differential inclusion, then for all x that are not equilibria, and for all f in capital F of ln x, this product is negative. And the proof is more or less by definition. So if you have good definitions, then they help you. So yeah, so let's call the logarithm x over x star u. Then this lies in the cone C E, but without S orthogonal because it's not an equilibrium. F lies in F of ln x over x star, but which is this? The relative interior of an intersection of polar cones. Now you have something that lies in the cone times something that lies in the polar cone, so in the interior of the polar cone, so you get a strict inequality. So UTF is smaller than 0. And we have shown that the entropy as a Lyapunov function helps us, or proves the asymptotic stability of equilibria of binomial differential inclusions. And my understanding of this is, so to speak, the ultimate use of the entropy as a Lyapunov function. It cannot do more. It helps to show the asymptotic stability of binomial differential inclusions, which embed mass action systems. But it's also quite easy to see that you cannot embed generalized mass action. So generalized mass action, you cannot use the entropy as a Lyapunov function for generalized mass action. The entropy works exactly for mass action, and it's a kind of a miracle why it works, but it does. Yeah, that's already about it. Just if you are aware of George Gratschon's work about toric differential inclusions, maybe just 2 words about a comparison. I mean, these binomial differential inclusions were introduced to deal with local stability and exactly of complex balanced equilibria. So the toric differential inclusions are designed to show global stability, like to address the global attractor conjecture or persistence conjecture, permanence conjecture. Also, they embed more complex ODEs. So, for example, that the rate constants can vary with time. But this also leads to certain uncertainty regions in these hyperplane arrangements or polyhedral fans. And also, I'm not so sure if the interior is used. So they have, I would say, generally speaking, the toric differential inclusions are a bit more complex from the motivation and also from the technicalities. But they also have kind of different purposes. Like in the global stability, you want to stay away from the boundary, so to speak, but you don't really care if you go to an equilibrium or there is another attractor in the middle somewhere, right? But the binomial differential inclusions help you to show really the asymptotic stability of a particular equilibrium, which I'm not sure if the toric differential inclusions do it. At least I think they're not designed for it. Yeah, so just to summarize, we have shown asymptotic stability of binomial differential inclusions, which of course implies asymptotic stability of complex balanced mass action systems. We knew that before. Also, it's quite easy to see how to embed detailed balanced enzyme systems into that, which are also called sometimes generalized mass action kinetics. But so there are several meanings of that. Yeah, then for sure one can also embed other classes. I have not really tried that much. For weakly, not just complex, for weakly reversible, it's unclear to me. Also, I have not thought enough, I would say. For sure, these results don't really help for generalized mass action, for the reasons I said already before. Now, another application, I already mentioned it in the beginning, of the new decomposition of the graph repression, these monomial evaluations orders, was linear stability of complex balanced generalized mass action systems. That's technically a bit different, right? There one computes the Jacobian, and so yeah, that's a bit different story. So what I don't know at all is what this means for graph theorists or people interested in linear dynamical systems like probabilists. But yeah, I'm not sure if anybody from this field is here. Okay, so I stop here and thank you for your attention.
Thank you, Stefan. And now I will stop recording here.